In this lesson, we are going to solve some problems on radioactivity. First problem, at time t equal to 0, the number of nuclei of a radioactive substance are 100 is given. At t equal to 1 second, the number becomes 90. What is the number at t equal to 2 seconds? Some of you may think that in the first second 10 nuclei is decayed, next second 10 nuclei will decay. That is wrong. Answer is not 80. Remember, in equal time, equal fraction of nuclei decayed or equal fraction of nuclei survive. So in this problem you see, in the first second, 90% of the nuclei have survived. So in the next second, 90% of 90, that is 81 nuclei will survive. That's the easiest way to solve the problem. Or you can think 10% have decayed in the first second. So 10% of 90 will decay the next second, that is 9, and N2 becomes 90 minus 9, that is 81. So very important, in equal time, equal fraction of nuclei are decayed. Next problem. At t equal to 0, the activity of a radioactive substance is 1600 becquerel. At t equal to 8 seconds, the activity becomes 100 becquerel. Question is, find the activity at 2 seconds. Now you can apply radioactive decay law, but the easier way of doing this is using the fact that every half-life activity becomes half. So R8 will be half to the power n into R0. Every half-life activity becomes half. Therefore, R8 is 100, half to the power n. R0 is 1600, right? Therefore, half to the power n becomes 1 by 16. That is half to the power 4, right? So there are 4 half-lives in this 8 seconds. 4 half-life is 8 seconds. So 1 half-life will be how much? 2 seconds. So 2 seconds is half-life. So in 2 seconds, activity will become half. So R2 will be R0 by 2, that is 800 becquerel. So from here we learn a very important thing. Every half-life activity becomes half. Every half-life number becomes half. And in the previous problem we learned that in equal time, equal fraction of nuclei are decayed. In equal time, equal percentage of nuclei survive. If you remember these two things, you can solve any basic problem on radioactivity. Now, let us look at one more problem on radioactivity. We have to prove that the mean life or average life of a radioactive substance is 1 by lambda. We have to prove it mathematically. At time t equal to 0, there are n0 number of nuclei. Okay? At time t equal to t, the number becomes n. At time t plus dt, the number becomes n minus dn. And at time infinity, the number is 0. Now what is the life of this Dn nuclei that are decaying between t equal to t and t plus dt? Not dt. What is the life? Suppose a person dies between 80 years of age and 80.001 years of age. What is his life? 80 years, not 0.001 years. So life of this Dn nuclei is time t. T and t plus dt are almost same. So life of Dn nuclei is t. Right? How to find the average life? Suppose 5 people live for 8 years of age. 10 people live for 85 years of age. And 20 people live for 90 years of age. So what is their average life? You'll multiply this number with this age. 10 with 85, 20 with 90, and add them all up and divide it by the total number of people. So in this case, to find the average life, we'll integrate, because that is a continuous thing, that was a discrete thing. We'll integrate T Dn, okay, Dn nuclei have a life of T, and integrate this from initially N naught nuclei are there and finally 0 nuclei are there, right? And in the denominator, we have to put integral of Dn, the total number of nuclei, from N naught to 0. This will give us the average life or mean life. Now this we can integrate very easily. This we cannot integrate directly because here t is there, here n is there. So to express this as a function of t. So now we know that minus dn dt is what? Lambda n, right? So therefore, dn becomes minus lambda n dt, right? So therefore, dn can be written as minus lambda n dt. And what is n? N is nothing but n naught e to the power minus lambda t dt, right? So this dn, we can put it in this equation. So t average becomes, the bottom integration is very easy, minus n naught. Here lambda is a constant, n naught is a constant. Only variables are these things having t. So lambda and n naught, along with the minus sign, we can keep it out of the integration. And we get integration of e to the power minus lambda t here and here t. So t e to the power minus lambda t dt. And that we integrate from 0 to infinity, because time varies from 0 to infinity. Number changes from n naught to 0. Time varies from 0 to infinity. This n naught gets killed. Minus sign also goes. So we are left with lambda and this integration. This integration is the product of two functions. This integration we can do by parts. How to do integration by parts? We first of all decide which function is the first function and which is the second function. First function should be easy to differentiate, second function should be easy to integrate. And for that there is a simple rule, I late. This is the rule. Okay, always I get late, so I late. First one is inverse trigonometric function. This one is logarithmic function. This is algebraic function. This is trigonometric function. E is exponential function. Exponential functions are always easy to integrate, right? E to the power x is a very nice function. You integrate that, you get e to the power x. When you differentiate e to the power x, you get e to the power x. Plus c obviously you get, but Integration is very easy. So here, this is an exponential function. So this will integrate and this will differentiate. Now, we'll integrate this by parts. Integration by parts is, we write the first function, this one, multiplied it by the integral of the second function. Then we put a minus sign. Then we integrate the product of differential of first function, which is 1, multiplied by integral of second function, which will be e to the power minus lambda t by minus lambda dt. And we write the limits here. This is 0, infinity. So see what we have done. First function into integral of second minus integral of differential of first function, which is 1, so that's why I did not write that. And integral of this is this. And this again you have to integrate. So what do you get? Lambda e to the power minus lambda t will come here. This t is already there, divided by minus lambda. And this again we have to integrate, so we get e to the power minus lambda t by minus lambda again, that becomes lambda square. 0 to infinity. Now when you put infinity here, this will be 0. When you put 0 here, this will be 0. So this whole term is 0. When we put infinity here, we get 0. When we put 0 here, we get 1. So what do we get? The average life. Lambda into 1 by lambda square. Minus sign will come because we are putting the lower limit. So minus minus will become plus. So what we get? 1 by lambda. So the mean life or average life of a radioactive substance is 1 by lambda. How we derive this? At t equal to 0, the number was n0. At t equal to t, the number became n. At t plus dt, the number became n minus dn. So this dn nuclei have lived for time t. These two are almost same. So life of dn nuclei is t. At infinite time, obviously the number is 0. So the average life is given by integral of t dn from n0 to 0 divided by integral of dn from n0 to 0. The bottom integration is very easy and direct, minus n0. For the top integration, it will replace dn by some dt. That we get from this equation. Minus dn dt is lambda n. So dn becomes minus lambda n0 e to the power minus lambda t dt. This we substitute here. Take out all the constants outside. Then we get an integration of product of two functions. We integrate that by parts. First function into integral of second minus differential of first function multiplied by integral of second. And then we put the upper limits and lower limits. Upper limit is infinity, lower limit is 0. For both the upper and lower limit, this is 0. For the upper limit, this is 0. For the lower limit, this is 1. So finally we get the mean life or average life of a radioactive substance is 1 by lambda. Just practice this once or twice and you'll find it very, very easy.